by delving into the concept of the order of a group and order of an element. How do we define it precisely?
The order of a group refers to the number of elements it contains. Meanwhile, the order of an element is the smallest positive integer such that raising the element to the power yields to the identity element.
To clarify the order of a group, consider a cyclic group generated by the element of A. If we repeatedly apply the group operation to A, the order is the number of distinct elements we encounter. Now, the order of an element, say B, is the smallest positive integer of K, such that B to the power of K equals the identity element.
Certainly. Let's take the group of integers module 6 under addition as an example. The order of the group is 6, and if we take the element 2, its order is 3 because 2 plus 2 plus 2 brings us back to the identity element.
Third performance test, second objective. Structures and characteristics of different subgroups. Now, let's get moving onto subgroups. They're subsets of a group that form a group themselves. How do we identify different types of subgroups?
So, we could consider cyclic subgroups, which are generated by a single element, and there are also proper subgroups, which are not equal to the whole group.
Precisely, Nisaya. Consider the group of real numbers under addition. The subset of integers forms a subgroup, right?
Yes, that's a subgroup because it's closed under addition, contains the identity element 0, and has inverses for every element, the negative of each integer.
And if we consider the subset of positive real numbers, that wouldn't be a subgroup since it doesn't have inverses for all elements.
Our second objective is assessing and justify whether a given set is a subgroup. So, my objective is to assess and justify whether a given set of elements together with the binary operations is a subgroup. To assess whether a set is a subgroup, what criteria do we need to consider?
The set must be closed under the group operation, contain the identity element, and have inverses for all elements. How do we rigorously prove? The set must be closed under the group operation, contain the identity element, and have inverses for all elements. How do we rigorously prove that a set satisfies this criteria?
So, we can use the subgroup criterion theorem or directly verify each property. So, let us say we have a set of 2x, 2 matrices with determinant 1. Is it a subgroup or a general linear group?
We need to check closure under matrix multiplication, the presence of the identity matrix, and inverses for each matrix. If these criteria are met, it's a subgroup. And providing the counterexample can help disprove it. For instance, a set of all 2 by 2 matrices wouldn't be a subgroup due to the closure issues.
The last objective, let's focus on proof techniques for propositions related to group theory. So, what are some common approaches?
Direct proof is a straightforward method where we establish a proposition step by step.
What about proof by contradictions? How does that apply in abstract algebra?
We assume the proposition is false and then derive a contradiction from that assumption.
Consider the proposition, in a group, the identity element is unique. How would we prove this?
We can use a direct proof. Assume there are two identity elements, E1 and E2. Then show that E1 is equal to E2 based on a group action.
Agreed. Alternatively, we could use proof by contradiction. Assume there are two identity elements and then derive a contradiction by showing they must be the same. And in conclusion, through active participation and collaborative problem solving, members enhance their understanding of group theory, subgroup structures, and proof techniques. The discussion emphasized the importance of clarity in defining concepts like the order of a group and the order of an element, as well as the criteria for assessing whether a set constitutes a subgroup. And also, the members have engaged in practical examples and proposed methods for rigorous proofs, including direct proof and proof by contradiction.